Good day, sir. Today, I'll be walking you through the main GUI code of my Python application, which is designed to solve nonlinear equations using various numerical methods. And the methods accessible through a clean, user-friendly interface built using tkinter. This main entry point, this one, kaning roots that and 5. And this main entry point of the application, it serves as the central GUI where the user can select one of 5 methods: incremental search, bisection, false position, Newton-Raphson, or the second method. Here I am importing separate GUI classes for each numerical method. Each one is stored in its own file, allowing for modular and organized code like this. Can store na separate, and then the window numerical UI class initialize. The main window, I set a title, a size, and the background color. It uses tkinters or tk like this to create the root window. And the build UI, this one method sets up the GUI. It adds a container, a title label, and a series of buttons. Each button corresponds to a different numerical method to make it visually consistent. I styles the button using TTK style. This one. TTK.style. And kaning sa ubos, this list of types defines the method, name, and the function to call when the user clicks the corresponding button. When a button is clicked, it triggers a method that opens a new window for that specific numerical method. And then each of these functions creates an open new GUI window for methods like Newton-Raphson. Second, I use tk top level to spawn separate child windows so users can work in multiple methods independently. And this final line ensures that GUI runs when the file is executed directly. It creates an instance of the main UI and launches the tkinter main loop. Then right now, we will run the file. Here, when it shows learning, runs our program. Then now we'll proceed to incremental method. I will explain it. So now I will explain the incremental method na parts. And then this one, the diff preprocess function, it cleans the function string input, replaces constant like pi to ingani nga symbol, and formats expressions. And then the insert multiplication sign adds multiplication symbols where implicit multiplication appears in the input. And then for this one, for I in range, it checks if product less than 0, sign change, or exactly 0. So ira na to ang code, then kanang maghatag og example like this. we will click the compute button. So mo ni siya ang gawas nga root. When you click the compute button, the program will evaluate the function at increments starting from 1. Sorry, and it detects where the function changes sign between points. It stops and highlights the interval containing the root and display results in the table. So the root is kaning root out is 2 x equals 2 will be detected because of x 2 equals 0. Simura to, sir. Good day, sir. For now, I will tackle about the bisection method. This application solves for the real roots of a nonlinear function using the bisection method. A reliable bracketing technique, the GUI allows the user to enter a mathematical function f of x at interval a, b, a step size to divide the interval, and it computes and displays all roots found within that range. GUI setup tkinter bisection this one bisection method up tk.top level creates a new window when launched from a main menu. Inputs f of x, a, b, and step via text entry widgets. Plot area and results table are created using matplotlib, this one, and ttk.triview. And then for this one, def bisection iteratively halves the interval where a sign change occurs and stops if the function value f of c is close enough to 0 or interval width is within tolerance. For find roots, diff find roots uses the step size to divide the interval a, b, applies the bisection method for each sub-interval of x sub 1 and x sub 1 plus 1 where a sign change is detected. For graph plotting, plots the entire function over the interval. Roots are marked with red dots and labeled. Table display shows the iteration table step-by-step values of a, b, c, and f of c for the first root only. Uses ttk.triview to list each iteration clearly. So, mag-example na to. This one. I will click this button sa kung hindi ka ni siya sa main, and then mo ni siya ang magawas. So I will calculate this. Mo ni siya ang magawas, sir. This polynomial is known to have a real roots at x equals 1, 2, and 3. The function scans intervals 0 to 0.5, 0.5 to 1.0, 1.0 to 1.5, until 4.5 to 5.0. In subintervals where a sign change is detected, example f to 0.5 less than 0 and f is 1.0 to greater than 0. It applies the bisection method to narrow in on the root. Output found Found roots displayed as this one. Graph the plots the function curve and labels the roots with red dots. Money, and the table shows the bisection iterations for the first root, A, B, C, and FC per step. So the step divides the interval into smaller brackets to detect all roots. Without this, only the first or the single root might be found. So what does the tolerance do? The tolerance value controls how accurate the root needs to be. A smaller tolerance gives more accurate results but may take more iterations. So that's all for the bisection method, sir. Thank you. Good day, sir. Now I will tackle about the false position method. This GUI application solves nonlinear equations. It's written in Python using tkinter for the interface, SymP for symbolic math, and matplotlib for plotting, and the user enters a function interval and tolerance to find one or more roots. So we'll start from the import this tkinter's handless GUI creation. NumPy is used for numerical processing and array handling, and matplotlib allows function plotting inside the GUI. Then SymP lets user input a symbolic functions like x square of 3 minus x, which gets converted into a numerical function with lamtify. And then so this class false position app initialize the application window, sets up labels and input fields for the function, interval A, B, tolerance, and number of subdivisions, adds a plot area using matplotlib, and then this one, the define false position, implements the regular falsy method, finds a root in the interval AB using linear interpolation, stops when the root approximation is within the tolerance or after the max iterations. And so the define find roots reads and validates. User inputs converts the function string into a numerical function f of x and splits the main interval into subintervals and checks for sign changes indicating a potential root. Calls a false position for each valid subinterval and filters duplicates to show only distinct roots, and displays results as a plot and a message box. Not this one. And this area for the plotting results clears the plot area and plots the entered function and marks roots with red dots, annotates roots with their coordinates. So I will now give an example for the false position method. This one. So example is x minus 2, and then we will start at 0 and we will end at 5. And for our tolerance, we will input the 1 minus 5, and then we'll click this find roots. So sa ato ang nakita, root found at 1.52138, and the graph shows root marked on the curve, shows iterations used to reach the root. This confirms that there's a real root between 1 and 2 where the function crosses the x-axis. So that's all for the false position method example and explanation how it works. Thank you, sir. Good day, sir. So now we will tackle about the Newton-Raphson method. This is my code. What does Newton-Raphson does? So GUI for solving equations using Newton-Raphson method. Users enter a function and arrange. The app finds real roots, shows iteration tables and graphs, and allows exporting results. So this part, the define Newton-Raphson, uses Newton-Raphson formula to find a root for a starting guess. And then the next one is define, find multiple roots, scans the range, finds sign changes, then applies Newton-Raphson to estimate root. Define, plot graph, this one, plots the function and highlights detected roots. And define display tables, this is shows iteration data in a table for each root. And I have also this one, export to Excel and export to PDF. Lets you save results as Excel or PDF file. So later I will run it and I will show you how to export it. And the last one, the run Newton GUI. Main function triggered when find roots is clicked. Gathers input, find roots, updates the GUI. So now we will run this and I will give an example. I will click this button, this one. So now I have the example, this function, the range start at -5, or I will change it to 0, then I will click this find roots. So here it is, the results, and this is also draggable, so you can see this part here. I have also these guide instructions on how to use this. So see the roots, graphs, and iteration tables. So now I will teach you on how to export. So one, export Excel. So we'll try Numericals. Save. So this is the saved file, Excel. Here is the result. And for now, I will also export into PDF. Okay, root PDF. Okay, then so we will now see the downloaded PDF file. So here it is. We'll open this one. And here is the result of the PDF file we download. So that's all for the Newton-Raphson explanation. Thank you, sir. So for now, I will discuss about the second method. And so let's start. This section, the define in it is about initialize. So it initialize the main window and layout, inputs, table, and graph. This one, the create input section, sets up input fields like function, range, tolerance, and iterations. And this one, the define run second, parses inputs, scans the range, and applies the second method to find all roots. And the define second, core logic of the second method, iteratively computes root approximation. And the last one, the define show results, displays the iteration table and graph with labeled roots. So for now, I will give an example for this code. I will click this button, and here it is. This is our example, so I will click this find roots. But before that, we have an instructions here. Then we'll click this. Click this find roots. So our equation here are the range start from 0 and it ends with a range of 4. Our tolerance is 1e minus 6 and our max iterations is 100. So this polynomial has known roots at x equals 1, 2, and 3. So the GUI scans the range 0 4 for subintervals. It applies the second method in each subinterval to find a root. If a new root is found, not already close to a previous one, it is saved. The table shows iterations x0, x1, x2, and x2, and the graph plots f of x with root markers. That's all for the second method explanation and how it works. Thank you very much.